And there are many more near-term experiments and demonstrations that are planned for that type of thing. And so that's a very near-term possibility. And I think we'll gain experience with that because it's still very large scale, but not anything close to a space elevator. And so using tethers in connection with the moon or Mars even, or asteroids, has a real more near-term potential.
One of the things that's come up in our research are the NASA Institute for Advanced Concepts funded studies. The space elevator studies by Bradley Edwards and Jerome Pearson. So that institute is now the NASA Innovative Advanced Concepts Program.
Yes.
Other than the structure being different, are the mission and goals of the program and what it funds different now?
It's very similar. It was a popular program. When we got involved with the early constellation program, the priorities were seen to be different, and that went away. It's now been brought back. One main difference is that before it was only managed sort of as an independent institute outside of NASA, and actually NASA projects couldn't participate. In fact, I was working on a project back about 7 years ago, and we wished we could have participated in that, but we couldn't because it was only for external activities. So now it includes NASA activities along with others, and it's managed more directly by NASA. But otherwise it's very similar. The one difference might be that they were really looking for things 40 years and beyond in the original institute idea. Now it's more 10 to 40 years. So it's still long-range concepts, but not quite so far-ranging. Hoping to get maybe some success stories from projects a little bit sooner than later.
So from what I understand of exploring the NASA website and your bio there, you work with the early stage innovation, which includes ENIAC, is it how I read it, the acronym, the Space Technology Research Grants, the Small Business Innovation and Technology Programs, and the Center Innovation and Centennial Challenges. Can you tell us about the kinds of projects you work through with the different programs and what the different purposes of the programs are?
Yeah, I can talk about those. We've reorganized a little bit even since then. But those were all the early stage innovation programs. So I had been involved with Centennial Challenges, which is our prize program. That's really our most unique program, where we just put prize money out and let independent teams take on that challenge without any management by NASA. And then they only get money if they're successful, and only if they're the most successful in a competition. So that's been very interesting, and we've had a lot of success with that. The other programs also are the more early stage kinds of things. One is NIAC that we were just talking about, NASA Innovative Advanced Concepts, for the long-range concept development. And those are small grants to do those kinds of projects. And then there's a fellowship program. The Space Grants is for graduate students to be supported for projects, research projects of interest to NASA. And then the Small Business Innovative Research Program, which is a very large program, really our largest, which is contracts that go to small businesses pursuing development of early stage technology that hopefully will find a customer either within NASA or in other government agencies or commercial space industry. So that's a collection of programs. And this office, the Office of Chief Technologist, has those plus several others that go a little bit beyond. The one I'm managing now involves small spacecraft technology. And when we say small, larger than 100 kilograms, and going down most typically to the CubeSats, which are 4-inch cubes, or maybe several of them hooked together. which is sort of a whole new effort. There's a whole community of people using these satellites, and it's something on a scale that universities can build satellites, small businesses, even individuals. And so we think that opens up a whole new world of research, and so we're trying to promote that. NASA hasn't been as deeply involved in that because we're generally involved with large spacecraft, but we're getting more involved in that now. And then we have other programs for game-changing technology to promote things that are very new, and that things that would change the way we do things. And then technology demonstrations, which is to take relatively new things that may not have a home within a particular program, like the space station or new launch vehicles that are large programs in NASA, but would be of value across, many programs, and both inside and outside of NASA. So we're trying to, attack the broad range of things, from early concepts to ones that are almost ready to go be tested in space, and everything in between, and reaching out to, not only the large aerospace companies, but smaller businesses, individual inventors, university researchers, other government lab researchers, things like the Department of Energy labs, those kinds of places, and and look for solutions not only from the typical places, but from non-traditional sources as well.
About the game-changing technology program, they gave a recent grant to STAR Technology and Research for their electrodynamic debris eliminator, which is, so the principal investigator for that is Jerome Pearson, who is the modern independent reinventor of the space elevator concept. And since that involves tether technology to clean up space debris, if that project progresses, what could that mean for the space elevator development, since the space debris is both a problem and the tether, sort of working with tethers would also sort of advance the space elevator effort?
Yeah, well, the concept in that project is the electrodynamic tether, which is a tether, a cable that can conduct electricity. So therefore, as it moves through the magnetic field of the Earth, as it orbits the Earth, it can use that force that is generated electrically as a force to move the whole collective spacecraft, which is, the cable and the spacecraft on either end of it around. So it can maneuver without using propellant, which means it can go on almost, indefinitely without being refueled, to go pick up something and then lower its orbit and then let it go so it falls and burns up in the atmosphere, or is recovered and somehow recycled or reused. That technology, of course, has lots of ways we could use that for moving things around in orbit. And what it would do is, on a large scale, but a smaller scale than a space elevator, give us more experience with tethers and understanding some of the issues with that, and gain confidence, maturity in the use of that kind of technology. So it's an exciting thing that we'll see. These things are all somewhat high risk technology, development work, and doesn't mean everything's going to work, but you learn by doing it, and you can study these things on paper forever, and you never quite know what's going to happen. This takes it out into the real world, and you see what does happen, and you learn a lot from that, whether it works or not. You learn, a lot more. So it's an exciting thing, and it's interesting. Jerome Pearson is one of the early proponents of the space elevator concept, and so a very creative individual.
That's a lot of that.
I guess my question I would have for you is, for the power beaming technology, which I saw is a little further along than the cable technology.
Yes,
Someone
yeah.
actually won that
Yes,
challenge.
exactly.
Can you just explain sort of the rough edges of how that works exactly?
Yeah, it to me, it was one of the most interesting things I've been involved with at NASA because, the idea is you use a laser to transmit electrical power through the air, without wires, to a device at the other end that uses that power. The way it relates to the space elevator is the idea that you wouldn't pull a cable up and down like you might do in a pulley on an elevator, because then you'd be moving twice the weight of the cable. So the idea is it would be self-propelled and it would just climb the cable. So knowing that we didn't have a cable that could go out that distance, we could still demonstrate that part of it, which is the power transmission from the ground. And of course, the reason you want to transmit the power is you don't want to have to carry all of that on board the object that's trying to climb. So an allied organization, an outside organization we worked with, really set this up. And they started with just a crane and a 100-foot cable, and people came out, and originally they were mainly using sunlight and mirrors and solar panels to drive their little robots up these cables. And then it progressed to 100 meters, and then the last version that we did, and no one won those early ones, but they did pretty well. And so, the goal kept getting raised, and the prize got raised. So there was a $2 million pot the last year that we did this, and a 1 kilometer cable. And the biggest problem, of course, is how do you even set this up? You can't get a crane. So they considered a balloon, but there were a lot of problems with that. Ended up using a helicopter. And what made this interesting is no one had ever done anything like this. There have been helicopters connected to the ground with cables, but not 1,000 meters up. And so that's what we did. We went out to the Dryden Flight Research Center at Edwards Air Force Base, a big dry lake bed where they do all kinds of experimental aircraft testing. Is where the shuttle originally landed, and flew. It took several attempts. We broke 2 cables in the early testing. We got ultimately a very good helicopter pilot, and he practiced a little bit, and raised this cable up, and it was somewhat like a space elevator because you could see the cable in front of you and go up for a little ways, and then it disappeared. Occasionally you get a glint of it in the sun, but you couldn't see the top of it, and you could barely see the helicopter. If you didn't know it was there, you wouldn't have noticed it. You couldn't hear the helicopter. So it was just a cable going up into the sky. It was quite a cool thing to see. And then these teams had, this point they had progressed from sunlight and mirrors to laser, fairly high power laser systems. And then they had their beaming trailers on the ground, and they would, we raised it up 100 feet to the starting point, and then they beamed their laser beam on the panels on the bottom of this robot, and they climbed. And we had 3 teams trying. 2 of them were fairly successful in climbing quite a bit. One got very close. The other one just completely nailed the challenge, at least at the first level, which was a speed of at least 2 meters per second. So they won $900,000. They climbed all the way to the top at an average speed of actually about 4 meters per second. If they had reached 5, they would have won the full $2 million. And they got close to that too. They only had a little glitch that prevented them on their last attempt from making that. It was quite a thing to see. There's some wonderful videos on the internet of that activity, set to music, which is quite interesting. So it was a great thing. We weren't really able to repeat it. This program we only fund the prize money. The challenge activities have all been run by nonprofit organizations in partnership with us. So it was very difficult to put this together again. The helicopter operations, for one thing, were expensive. And he would go up hold position for 45 minutes, and the cable barely moved. It was the most amazing thing. And he was up there with no references to look at. He used the GPS, and to hold his position, and a guy on the ground kind of giving him directions. But to do it again, just it was difficult to pull off. I think it was a one-time kind of thing, and so that second part of the prize was never won. And the team that won, they've really gone on to do lots of other things. One thing, they've demonstrated a little scale model helicopter that they run, for hours, off the ground, just beaming the power to it, and they could do it forever. They just got tired, but the system would just run forever without using any other power. So they have lots of ideas for things they'll do with this power beaming technology. The other thing we find, from NASA's point of view, you could have a rover in a dark crater, for example, going around, and you just had to send the power to it this way from a power station on the rim. You could power things from the orbit of the moon down to the surface without having to have the power supply there. Probably on Mars as well, and then beaming power from one spacecraft to another in orbit. You could do a lot of things with that. So that's another whole area that it has all kinds of potential, and we hope through things like these prize challenges we open people's eyes to what is possible. Doing things that maybe nobody bothered to do. It sounded too hard. It sounded too crazy. If we have a chance to do them, sometimes you find out that it's more realistic than anybody thought, and that's really what we hope to accomplish with these things.
I guess another aspect of the debate that I've only seen a little bit of, but I'm actually really curious about, is where you anchor it to the Earth. And sort of the two options are: you anchor it to the actual crust of the Earth, or you put it on some kind of floating barge boat situation.
Yeah.
What of that debate have you seen? I mean, what's the sort of sides there?
Yeah, the problem of anchoring the space elevator is one of those engineering issues that once you have a material that might work, then you really have to get down to how you do that. But, you want to be on the equator in order to take advantage of the position in orbit above that. So you look at it, a globe, and there's a lot of water. In the ocean might be the most reasonable place to do it, because you probably want to be in a place that's somewhat remote in case things go wrong. So a platform in the ocean seems like a good idea. You could be out kind of in international water, and I don't know if you may want to have some ability to move the base around a little bit and have some flexibility so you can absorb changes. In fact, that's what we did even for our 1 kilometer cable. We had 3 smaller cables connected in a tripod on the ground, and at the end of each of the short cables there was a heavy chain, and that absorbed any of the motion of the helicopter and the wind affecting the cable. But in the end, the pilot got so good that he could watch, and there would be one link of the chain moving a little bit. That was the stability, even in pretty strong winds. That kind of gives me the confidence that those kinds of technical problems that are not easy will be solved one way or another. Some way to absorb, the motions that would probably be there in the cable, at one end. The other end would be pretty stable because it's sort of following the laws of orbital dynamics. It's going to be very predictable. The other end on the Earth is much less predictable. So I think a platform at the equator in the ocean probably makes the most sense as a base of it.
Mm-hmm. And so once you get that sort of challenge done, I guess I'm sort of curious about what exactly the sort of ideal materials you'd be moving up and down the space elevator. I mean, once you actually get it constructed, what are you actually putting up there, and what's the goal for that?
Yeah, the goal is to replace the normal way of taking using rockets to take things up and down with this elevator that would take up, first of all, people. Now it would take you days to get there. It's more like an ocean cruise than a trip in a rocket. But there would be no unusual accelerations. It would be, you could sit in a chair and you could stand up, you could walk around. You would, it would be like you were on a cruise ship or something, or even on, maybe on an airliner. But so people up and down, and again, the return would not be the fiery, dramatic reentry that you normally have, but you just ride back down again like you went up. A little bit like riding, first time I went on a hot air balloon, I said this is like going up in an elevator. It's amazingly calm, and coming down can vary depending on what happens, but this should be a very predictable descent on the elevator. And then everything else we need, materials and equipment, which would not have to be now designed to withstand, the forces of acceleration in a rocket launch. You just take ordinary things and put them in there and take them up, and take them off when you get at the probably somewhere along the way you would, before you got to the counterweight, you would get off, and and of course most of what we launch into space now is, if we're going beyond Earth, is propellant for the rockets to go beyond. I'm hoping other research we're doing will reduce that, and we'll begin using much more efficient rocket engines that won't require huge amounts of propellant. But at least the way we look at things now, that's a big part of what we have to take up. If we want to go anywhere else, we need the fuel to take us there, and then food and things. What might end up happening, and you can imagine at this future point, perhaps a lot of what we'd be using it for is to bring things down. Things that came from resources that we were getting from asteroids or from the moon, being brought back to be used on Earth. Industries that might move to space where they would be have less impact on our environment. That begins to make sense if you have a way of moving them back, in a reasonable way at a reasonable cost. And again, that's something the elevator would enable. So it could almost sort of turn the whole thing upside down, where most of the traffic might be coming the other way. If we're now using space as a place to get resources instead of from the Earth, and using space as the real base for our industrial activity, and moving that off the Earth, which perhaps was never meant to support the kind of things we do, burning things, and you can do a lot of those kinds of things in a space environment without really impacting any biological kind of environments like we have on Earth. So it's a different world, and almost one turned upside down in the sense. That's kind of the vision of the science fiction writers like Arthur Clarke, and who was a huge influence on me from the early age, of the Earth being a garden, and all the industrial activity happening beyond the Earth. So, and it's hard to imagine that happening just with the kinds of rockets we use today, but that's not what we'll be using forever. So this is the kind of thing that enables that. So.
I guess one last question I would have is sort of more a fuzzy political question, but if you actually surmounted all these engineering challenges and could actually build a space elevator, is the next sort of biggest hurdle really just political? I mean, sort of figuring out who owns it, where it goes, what international organizations would cover, the sort of day-to-day maintenance, stuff like that. I mean, are those questions that really haven't been touched, because what's the point of it now?
Yeah, well, the political aspects, we've been a little bit surprised to see people actually addressing those, and we're saying, well, let's let's figure out how we might actually do this in reality before worrying too much. But that's not a bad thing, to think ahead of what it really implies, and it's probably not a simple question. Where do you put it? That you've now made a place on Earth extremely valuable now, because it's and vulnerable as well. You might want to have more than one of these, and there's probably some limit to what what makes sense. So it becomes somewhat of a critical resource then, and a critical asset. I think you would want to have international coordination and cooperation, because you don't really want to get into a competitive situation with such a critical and vulnerable asset in one or a few places. So, and it would affect, having these tethers running through low Earth orbit up to very high altitudes means that intersecting spacecraft have to be dealt with. They need to avoid hitting it, because it would be bad not just for them but for the tether as well, most likely. So there has to be a lot of cooperation to make this all work. And we have other examples of that kind of thing. It can be done, but it won't just happen by itself. I think you're going to have some kind of planning and coordination, and who owns it? Well, maybe whoever paid for it, but it's more complicated than that. Just because you can build it doesn't mean you have a right to tell everybody else to stay out of your way and decide what it costs to move things up and down, independent of everybody else's interest in it. So it is, I think, a complicated thing that we do need to think about as we get closer to the reality of it. And then the thing I mentioned is the cost. Who's paying for it? It would be far bigger than the biggest bridge ever built or the biggest building ever built. So it would be an enormous project. It would take a lot of capital to put it in place, and that becomes an important consideration. And whoever does pay for it will have a lot of influence over its operation, but they can't, again, operate without the cooperation of other people. So.
I guess I had thought one more question about just your opinion on the carbon nanotubes. We've heard through our research, I've seen estimates anywhere from 5 years to 20 as to when this technology will really be sort of usable. I'm just curious what your opinion.
Yeah, I don't I don't really have a good idea. I think it's like a lot of these things. It sometimes seems like things are always 5 to 20 years away, until they happen. Really, the carbon nanotubes sort of came out of nowhere, and then they existed, and they're still not really practical, but it could happen tomorrow that somebody makes a breakthrough, and that changes everything. But they're probably a few years away. I just don't know how far away. And there's a difference between making one that might be meters and meters long versus kilometers long. And so there may be more stages of development that are needed before we see anything on the scale of a space elevator. I think that we will see its use in other materials before that, used in building structural materials, long before we see cables going all the way to deep space. But
I just had some recording issue at the very beginning, so if you could just reintroduce yourself and maybe just say how the carbon nanotube just changed the whole deal and maybe.
Okay. I'll try to remember what it. Maybe you can prompt me if I. Yeah, but you can prompt me if I haven't said exactly the same thing. But yeah, my name's Andy Petro, and I'm an engineer here at NASA headquarters. And my background is in aerospace engineering, working in the Space Shuttle, the Space Station program with the Russians on the Soyuz for the International Space Station, and a lot of advanced projects. And then came here to headquarters 4 years ago to work on mostly public partnerships involving technology, like the Centennial Challenge prize program, and now in the small satellites technology programs that we have. The other question had to do with the carbon nanotubes, and the idea with carbon nanotubes provide a material that shows promise of being strong enough and light enough to do this job of supporting its own weight plus the weight of another object over a length of hundreds and thousands of miles. And so once you've developed that past the laboratory state we're in now, where you only have a few millimeter lengths, the ability to build things like that will affect every industry and revolutionize every industry, because we'll be able to make structures that are incredibly lightweight and strong. So you can imagine vehicles of every kind, airplanes, buildings and bridges, all being built completely differently than they are now, and that certainly will revolutionize our world in a lot of ways.
Thank you, that
Okay.
was great.
Yeah, thank you very much. That was perfect. Yeah,
Okay.